In this video, we're going to look at section 3.2, which is on the substitution method for solving a system of equations. So this is how the substitution method works. First thing you'll have to do is solve one of the equations for one of the variables. So I'm keeping that as broad as I possibly can. It doesn't matter which equation you choose, it doesn't matter which variable you solve for. So you just need to get one of the variables by itself on one side of the equation for one of the equations to get started. Oftentimes, that step will already be done for you. Step 2, plug that equation you just solved for a variable into the other equation for that particular variable. So you're going to do a substitution here. You're going to plug it in. And I'll show you how that works when we do the example. The examples, we're going to have several. And then once you've plugged that one equation into the other equation, the result you're going to get is a new equation with just one variable instead of two variables. So step 3 is to solve the resulting equation for that remaining variable that you have. And then step 4 is to take the solution you get from step 3, plug it back into one of the original equations, most likely the one where you already solved it for the variable, the other variable, and then find the solution for that last remaining variable. All right, so that is the process we are going to use. I apologize if it sounds a little bit too abstract at the moment, so let's make it a little more concrete by looking at an example. All right, so here we want to solve the following system of equations by the substitution method. So they're suggesting that is the way you want to do it, and that is indeed the easiest way to do this problem. What we're going to do is step 1, solve one of the equations for one of the variables, but if we look closely here, we realize that the second equation is already solved for x. So step 1 is already done for me. They already have an equation solved for a variable. So we'll move on to step 2. Step 2 is to take that equation that's solved for x and plug it into the other equation, the top equation, for that variable. So we're going to replace the x in the first equation with what it's equal to in the second equation, which is this part right here. All right, so I'm going to rewrite this first equation right here. We'll have 8, but in place of this x, I'm going to plug in 28 minus 6y. 28 minus 6y, because that's what x is equal to in the second equation. That's what we will replace x with in the first equation. And then the rest of the equation just gets written out the same. We'll have plus 5y equals 9. All right, so just to show you a little more clearly the substitution that just took place, we have 8x plus 5y equals 9, right? That's the first equation. We replaced the x in the first equation with what it was equal to in the second equation. Right. So what we have as a result is this new equation where both of the original equations are present at the same time. We still have 8x plus 5y equals 9 here. That was the original equation that was here. But we also let this equation know that in place of x, we have 28 minus 6y. So this equation now also realizes that x is supposed to also equal 28 minus 6y. So we have both equations present at the same time. So any information we get out of this equation will relate to satisfying both equations at the same time. The information we are going to be able to extract is what y is equal to, because now this equation only has the y variable. So now we can solve it for y. So that's step 3. So let me go ahead and enumerate my steps a little more clearly. So this was step 2, replacing x with 28 minus 6y, because that's what the second equation told us x was equal to. And then step 3 is to solve for the variable that you have. We're going to solve for y. We'll start by distributing the 8 into the parentheses, and right away we're getting kind of a big number here, so I'm not sure what that is off the top of my head. So we'll have 28 times 8. It's going to be 224 minus 48y, and then the rest of it just copies down, plus 5y equals 9. We'll combine like terms, so remember, be careful, this is negative, so we'll have 224 minus 43y equals 9. We'll go ahead and subtract the 224 to the other side to get y by itself. And I'll continue over here. So we'll have negative 43y equals negative 215. Oh, and hopefully this works out okay. Let's see. Yes, thankfully it does. Now, these numbers, not that it has to be a nice answer, But especially for our first example, I'm not expecting some crazy answers here. So if this did not work out nice, I'd maybe question my steps over here and wonder if I did something wrong. But the calculator assures me when I divide by negative 43 that you get a nice answer here. You get y is equal to 5. So negative over negative makes that positive, and this actually divides nicely, and we get y equals 5. So that's step 3. Step 4 is to take the answer you get from step 3, which is y equals 5, plug it back into one of the original equations. So I hate to make a mess of things, but I'm going to draw an arrow, and we're going to plug it back into one of these original equations, and it's our choice. We'll get the same answer from either equation, but we want to choose the one that'll be easiest to get the answer from, and that's going to be the bottom equation because it's already solved for the variable we're looking for. We're trying to find x, it's already solved for x, so we should use the bottom equation. So this will be step 4. We'll take this equation here, x equals 28 minus 6y, and we're going to plug in y equals 5 here. So we'll end up with x equals 28 minus 6 times 5, which will be 28 minus 30, which will be negative 2. Oops, sorry, that kind of came out funny, didn't it? Let's try that again. 2. Okay. So we get x is equal to negative 2. So to type our answer into Math Excel, it wants the answer as an ordered pair, just like we were doing in the previous section in 3.1. And remember, ordered pairs go in the order of x first and y second. So it doesn't matter the order you got the numbers in your work. For writing the answer, it needs to be the x value goes first, the y value goes second. So x is negative 2, so we'll put that first. All right, sorry, I must have done too much writing on this screen, or I went too fast or something because it's getting kind of laggy on me here. And y is equal to 5, so that'll go second. And so we get the point, negative 2 comma 5. All right, let's take a look at another example. All right, so same thing, solve this system of equations using the substitution method. This time, step 1 is not done for us. So we will have to take the time to carry out step 1, which is solve one of the equations for one of the variables. Again, in theory, it doesn't matter. You should get the same answer either way. It doesn't matter which equation you pick or which variable you solve for. And because of that, we should try to make things as easy on ourselves as possible. So while you could solve the bottom equation for y, I don't know why you would want to do that. That's going to make a pretty awful equation when you do that. You'll subtract 7x, divide by 13. It's going to be an awful mess over here that you would then have to plug into the top equation, and it's just going to be difficult. It's just going to be difficult all the way through. All right, so the easiest thing for us to do here would be to solve the top equation for y, because all it's going to take is adding a 3x to the other side, and everything stays nice and neat. So we'll take the top equation, negative 3x plus y equals 29. We're going to solve it for y by adding the 3x to the other side. And so we get y equals 29 plus 3x. All right, so this is step 1. Solve one of the equations for one of the variables. So you get to make that choice, but make that choice to make things as easy as possible on you going forward. Right? So now that we know y is equal to 29 plus 3x, we can move on to step 2, which is to plug this into the other equation. And we want to make sure you don't plug it back into the equation you just got this information from, because then you're going to draw the wrong conclusion. We just got this information from the top equation, so this needs to get plugged into the bottom equation. Use the equation that hasn't been used yet. So it's going to stay the same. We'll have 7x plus 13, but instead of y, instead of the y variable here, we're going to plug in 29 plus 3x. So I'll use a different color to make it really stand out. So this is where the y variable would have went. In place of the y variable, we're putting 29 plus 3x. The rest of the equation will stay the same, so we'll still have equals 9. Right. So that's step 2. Step 3 is to solve this equation for x. So we'll go ahead and distribute the 13. Again, we're going to get some big numbers here. We'll have 7x plus 13 times 29, which is 377, plus 39x equals 9. So make sure you multiply it to both of those. We'll combine like terms. Now be careful here. You do not have to subtract the 39x over here to match it up with the 7x, they're already on the same side of the equation, so we just combine them together. Right? It doesn't matter that there's something in between separating them. If they're already on the same side of the equation, addition is commutative, meaning you can move things around when you're adding. It doesn't matter the order you add in. And so we can go ahead and add these two things together and ignore the 377 for the moment. So we'll add these together and we get 46x. And then I'll copy down the plus 377 equals 9. We'll continue up here. So I'll have 46x plus 377 equals 9. We'll subtract the 377 to the other side. And we'll get 46x equals negative 368. And then we divide by 46. And again, I'm not expecting this to work out to be horrible. It could. In theory, this answer could be whatever. It could be fraction, decimal. There's no reason why it has to be a whole number. But I think Math Excel is going to be a little bit nicer to us than to give us such a horrible answer this early on. And so thankfully I'm right. We get negative 8. So it works out to be a nice answer. So that's step 3. And I really didn't leave any room for myself to do step 4. I didn't utilize the space over here very well. So I'm going to try to squeeze it in over here, but I didn't really leave very much room for that. So step 4 is to take our answer from step 3, which is negative 8, plug it back into one of the original equations. Now you could go back to the original problem that you were given and plug it into one of these two equations here, and you'll be fine. You'll get the right answer from that. You get to choose which equation to plug it into. I'm going to suggest the top equation because it just looks friendlier. But also, what we were given in the problem here is really equivalent to this. So this equation really is the same as this equation here. So why not plug it in where we've already solved it for y, since that's what we're looking for? So when I say plug it back into one of the original equations, it could be the very original problem you were given, or some derivative of that. So this is a derivative of the original equation, so we can use that as well, and that's fine. So we're going to use this right here. Y equals 29 plus 3x. We're going to plug in negative 8. If I can fit it in here, if it'll let me write. Plug in negative 8 for x. We'll get y equals 29 minus 24, which gives me y equals 5. So we get y equals 5 again. That's just coincidental. So to type this into Math Excel, we'll type it as an ordered pair. X goes first, y goes second. And that would be my solution for this example. All right, let's take a look at another example. We have solve the following system of equations by using the substitution method. We have x plus 8y equals 5, and we have x equals 7 minus 8y. So you'll notice step 1 is already done for me. The bottom equation is already solved for x. All right, and so we'll skip step 1. We'll use the bottom equation and plug that into the top equation for x. All right, so step 2 would be to take this equation, x plus 8y equals 5, and in place of x, we are going to plug in 7 minus 8y, because that's what the bottom equation tells us x is equal to. The rest of the equation will stay the same, and this one has an unusual outcome in that now when we go to combine like terms, they actually just cancel each other out, and we get 7 equals 5. So if that ever happens to you, if you're trying to solve the system of equations, and in the process your variables just completely disappear, your x and your y variable are both just gone, and you get just a couple of numbers here like this, and by the way, this is part of step 3, then you have a special outcome. You're not going to get just a single answer like we did on the first two examples. So it's either going to be infinitely many solutions or no solution. So if your variable completely disappears on you, it's going to be one of these two special answers. The way you decide which one it should be is based on whether this comes out true or false. So if your variables disappear and you get something that is false, like we did this time, right? 7 does not equal 5, that's false. That means your system has no solution. If it comes out true, if we had gotten 5 equals 5, that means there's an infinite number of solutions to the system of equations. And so that's how you'll tell the difference between those two special cases. Right? So this time it was no solution because it was false. If this had worked out to be a true statement, we would have selected infinitely many solutions instead. All right, so be on the lookout for those special outcomes. All right, so let's do the same thing here. We're going to solve this system of equations using the substitution method. Same thing. Step 1 is already done for me. They kind of wrote it backwards here, but this is already solved for x, right? Got x by itself on the right-hand side this time, but it is solved for x, so step 1's already done. We'll take what x is equal to here, plug it into the top equation for step 2. So maybe I'll do it down here. So for step 2, we have 5x minus 25y equals 30. Right? That's my top equation. But what I'm going to do is instead of x, we're going to plug in 5y plus 6, because that's what x is equal to in the bottom equation. So I have 5, so this 5 gets copied down. It gets multiplied to whatever x is equal to, and because there's multiple terms, we need to use parentheses around that. Minus 25y equals 30. Right? So we replaced the x with 5y plus 6. Everything else stayed the same, right? 25y stayed the same, 30 stayed the same. Now we're going to solve this equation. We'll start by getting rid of the parentheses, so we'll distribute the 5 here. We get 25y plus 30, and then the rest of it copies down, minus 25y equals 30. And so again, we're going to have a special outcome because this 25y cancels out with this minus 25y, right, when we combine those together. And so we end up with just 30 equals 30. So our variable has disappeared on us. Again, I don't know why I'm waiting to this point to remember this, but remember this was step 3. Our variable disappears on us, just like it did in the last example, except this time, the result we get is a true statement. And so if it's true, that tells me there's infinitely many solutions. All right, if this had worked out to be false, I would have said this was no solution. But because 30 actually does equal 30, that's true. That means the system of equations is not always true, but anything that works in the first equation automatically works in the second equation when this works out to be true. So there's an infinite number of solutions. Because there's an infinite number of things that work in the first equation, and any of those will automatically work in the second equation. Because the secret here is that these are actually the same equation. They kind of hid it from you by rearranging it and making the numbers a little bit bigger, but the equations are identical, which means anything that works in the first one automatically works in the second one. All right. Okay, so let's see, how much more do we have? We have one more example and then a word problem to talk about. So solve the system of equations by the substitution method. So this time, I think what's going to happen is we're going to get not such a nice answer. So near the end of the homework, you'll start getting solutions that might be fractions. And you want to keep them in fraction form. Don't write them as decimals. And I think that's probably what's going to happen here. The first step is not done for us either. So this is about the worst case scenario for these kind of problems. So what we're going to do is solve one of the equations for one of the variables. I'm looking to see which variable is going to be easiest to solve for. And I think probably the bottom equation, solving it for y, is going to be the easiest thing for us to do. Right? And so what we can do, you could subtract the 2x over here, but then you have to deal with that negative sign. What I think will be easier for step 1 is to add the y to the right-hand side. And that way we get rid of the negative sign. So we'll have 2x equals 5 plus y, and then we'll subtract the 5 back to the left-hand side. So get 2x minus 5 is equal to y. And that way you don't have to deal with dividing by a negative. So that's step 1, solving one of these equations for one of the variables. Step 2 is to plug that in to the other equation. So keep in mind, we use the bottom equation to solve for y, so this needs to get plugged into the top equation. So for step 2, we're going to have 2x plus 3y equals negative 2. Don't forget that negative sign there. A lot of students overlook that. We're going to copy everything down, 2x plus 3, but in place of y, we're going to replace it with 2x minus 5. And then everything else stays the same, so it'll still equal negative 2. So again, in place of the y variable, we're plugging in 2x minus 5 because that's what we have over here from the second equation for the value of y, right? So the second equation is telling me y equals 2x minus 5, so I'm letting the first equation know that. Taking the y away from the first equation, replacing it with 2x minus 5 as well. All right, now we're going to solve this equation. This is step 3. We distribute the 3 to the parentheses, so we get 2x plus 6x minus 15 equals negative 2. We'll combine like terms, and this time the variables don't cancel out on us like the last two examples. So we actually will get a solution here. We will add 15 to the other side, and we'll get 8x is equal to 13. And as I mentioned, I had a feeling about this. This does not work out to be a nice answer. Right? We divide by 8 on both sides, and we get x is equal to 13/8. That's going to happen sometimes. Again, it doesn't have to work out to be a nice answer every time. So that's what we get for x, and that wouldn't be so bad in and of itself, getting an answer as a fraction at the end of step 3, except that what we have to do is now plug that back in to one of the original equations to solve for y, and that's where it's really going to give us a hard time. And again, it's our choice. We can plug it into the first equation or the second equation. I think it'll be easier to plug it into the second equation here, where we've already solved it for y. So again, this is the same as the second equation, but it's already solved for the variable that we're looking for. So for step 4, I'm going to use the bottom equation, where it's already solved for y, to plug in this new value for x. So I'm going to take x equals 13/8, plug it in over here. So we'll have 2 times 13/8 minus 5 equals y. Think of this as 2/1. The 2 cancels out with the 8, leaves me with a 4 on the bottom. So I'm going to get 13/4 minus 5 equals y. Think of that as 5/1. We got to get a common denominator, which will be 4. So you multiply 4 to the top and bottom of the second fraction so that the denominators will match up. All right, so we get 20/4 there. And now we can subtract these, and we will get negative 7/4 as the value for y. All right, so that's step 3 is over here, step 4 is right here. Okay, so now we have our x and our y. So the way you type this into Math Excel is as an ordered pair, 13/8, comma, negative 7/4. Well, let's try that again. Okay, negative 7/4. All right, so hopefully that's somewhat legible. But that's the answer you type into Math Excel. All right, let's take a look at this word problem. Now, I know word problems can be scary, but they aren't really that scary in these sections. So these system of equation word problems really are not much more difficult than just the regular system of equation problems. The only extra difficulty here is finding your 2 equations. So instead of them telling you what the 2 equations are, you have to construct them. But most of the time, students do a pretty good job of putting these equations together. So let's look at this problem. Hockey teams receive 2 points when they win and 1 point when they tie. One season, a team won a championship with 57 points. They won 12 more games than they tied. How many wins and how many ties did the team have? So there's 2 unknowns here, right? We don't know how many wins the team had. We don't know how many ties the team had. Those are unknown values. And so we will use variables to represent those. And however many unknown values you have, that's how many equations you need in order to find a solution. So I will let x represent the number of wins, and I'll let y represent the number of ties. So there's 2 variables. That means we need 2 equations in order to solve this to get a solution. So we read back through the problem. They receive 2 points for every win and 1 point for every tie. And altogether, this team had 57 points. So to put that information together, if I take however many games they won, which I'm calling x, they got 2 points for each of those games. So I'll multiply it by 2. So if they won 5 games, they got 10 points altogether, right? You multiply by 2 to get the total number of points from that. Plus, they get 1 point for every tie. So we're going to take 1 times the number of ties they had. So 1 point for every tie. And you don't really need to write the 1 here mathematically, but I just want to emphasize we're taking 1 point times the number of ties they had, which we're calling y. And that tells me how many points they got for ties. So if they had 7 ties, they would get 7 points. 7 times 1 would be 7. So altogether, they earn 57 points. All right, and so that's one equation. 2 times the number of wins to get the total number of points from the wins, plus 1 times the number of ties to get the total number of points from the ties. You add those together to get their total number of points for the season, which we're told is 57. The second equation is going to be based on this information. They won 12 more games than they tied. All right, so the number of games they won, which we're calling X, is 12 more than however many they tied. All right, so if they tied Y games, which is what we're calling the number of ties, and add 12 to that, that will tell me the number of wins that they got, right? Because they won 12 more than they tied. Right? So if you want to maybe reword this, the number of games they won is equal to 12 plus the number of games they tied, which is what I wrote here. And that gives me my second equation. And now I can solve this system of equations. We'll use the substitution method. And step 1 is already done for me because we already have the bottom equation solved for X. We will plug that into the top equation for step 2. So we'll have 2x plus 1y, I'm just going to write y for that, equals 57. In place of the x here, we're going to plug in y plus 12. And if you wrote 12 plus y, that's fine too. When you're adding, the order you add in doesn't matter. Now, if it was subtraction, if it had said 12 less games than they tied, then you got to be careful the order you subtract in, and you would have to do it as y minus 12. 12 minus y would not be the same thing. All right. The rest of the equation gets copied down, right? So I'm copying down the plus y, copying down the 57, and then we solve. So from here, it's just like the problems we've already done in this section. We'll get 2y plus 24 plus y equals 57. And by the way, this is step 3, solving it for y. Combine like terms, we have 2y plus y. That gives me 3y plus 24 equals 57. And then we will subtract the 24 to the other side. So we get 3y equals, I feel like I should be able to do this, but my mind is kind of blank right now. So I'll just do this in my calculator. We get 33. Now earlier I was saying you can get bad answers, that's okay, but not for this word problem. For this word problem to make sense, we cannot get an answer that's a fraction or a decimal because you can't have 0.7 of a game that you won or 0.7 that you tied. It has to be an exact whole number. And thankfully, that's what we're getting here. So we divide by 3 on both sides, and we get y is equal to 11. So that tells me they tied 11 games, right? Because y was the number of ties. How do I find the number of wins? I complete the process for solving the system of equations. I take y equals 11, and I plug it back into one of these original equations. I'm going to choose the bottom one because it's much easier to work with. We'll plug in 11 for y, and we'll get that x is equal to 11 plus 12, which is going to be 23. And so this is the number of games that they won. This is the number of games that they tied. And that's what you'll type into Math Excel. So how many wins did the team have? They had 23. 23 wins, and then it'll ask how many ties, and you'll type in 11. All right. So that's how the word problems tend to work in section 3.2, and also we'll see a very similar kind of word problem in section 3.3. All right, so that concludes section 3.2 on solving system of equations using the substitution method.